Welcome to Lecture 2, The Amazing Disc. This is the beginning, really, of Module 1, entitled Sight and Sound, and it's an exploration of the physics of light waves, particularly, and sound waves as they apply to a number of everyday phenomena. And the first lecture, The Amazing Disc, begins with an investigation of the common medium of the compact disc and the digital versatile disc, or DVD. I have to say that the idea for this first lecture in this module came from a colleague who's a poet who also loves classical music and has his study instrumented with an enormous array of powerful stereo equipment, and he believes that the compact disc is the most significant invention of the 20th century. I'm going to disagree with that in Module 4, but one could argue strongly for that. But I've decided to make this first lecture about the compact disc and its cousin, the DVD, because in a sense these objects are metaphors for almost all of physics. Almost all areas, almost all realms of physics that I described in the first lecture are involved in making CDs and DVDs work. Everything from quantum physics to optics to mechanics to electronics and so on. So this is really metaphorical in a sense, and at the beginning we're going to raise more questions than we answer, and then we'll answer some of these here in this lecture and some in subsequent lectures. If you're one of those very old-fashioned viewers who's looking at this course on VHS tape, don't be offended. Your medium will come up in Module 3, and we'll understand how that works. But here we're going to be stressing the DVD and the CD as media for storing information, both audio information, video information, data, computer information, and so on. Let me just begin by pointing out a few things that discs do. Here's a disc, this wonderful little 5 1/4 inch circular thing, plastic thing. Some things that they do that help us to see which realms of physics are involved. First of all, discs rotate. They rotate remarkably at speeds which vary. It's not like the old 33 RPM or 45 RPM records that I'll get to in a few minutes when I do some history, but they rotate at speeds that vary. Why do they do that? Discs are an optical storage medium. Now, what I mean by that is not that they can be used to store your digital camera images, although they can, or that they can be used to store whole movies, they can, or that they can be used to store little QuickTime video clips on a regular CD, they can. What I mean is that they store and retrieve the information by means that involve the principles of optics. That's true whether the disc is an audio CD that's playing music, a video DVD that's playing a movie, computer data, computer programs, software, whatever. These are still devices that are storing the information optically. So they're an optical storage medium, and as such they involve properties of light like reflection, refraction, interference, all properties that we'll cover in the next lecture. How do we get the information off the disk? Well, we get it off it optically, but then what do we do with it? We process it electronically. These days that means using semiconductor-based electronic circuits. How do those work? Well, that's the subject of Module 4. Disks deliver to us ultimately sound and visible images, or they deliver data to our computer, but when they're delivering sound and visible images to us, that means we have to form the images on the backs of our eyes, our eardrums have to vibrate, we have to hear the sound, we have to perceive the sound, we have to focus the images. How does that all work? So almost every aspect of getting information on and off a CD or DVD involves a wide variety of principles of physics. Before I go into how these things work, and that will be the main topic of this lecture, I want to give you a little bit of history, because these are far from the first devices on which we've stored information, and I've chosen to focus only on devices we've used to store primarily audio information. We could go back further and talk about clay tablets and early writing and so on, and I'm not going to go that far back. It was Thomas Edison who invented probably the first audio information storage device. He had a wax cylinder. He had a needle connected to a large sound capturing chamber. The sound waves vibrated the needle. The needle cut those vibrations into the wax cylinder, and as the wax cylinder turned, that information was recorded on the cylinder. To play it back, the opposite occurred. The grooves in the wax cylinder vibrated the needle, vibrated a diaphragm in this big speaker-like device which produced sound waves. And you've probably seen pictures of these ancient devices. Something not much different from the ancient wax cylinder is the used-to-be modern phonograph record. Here I'll date myself. And the phonograph record is really Edison's wax cylinder with the grooves now stamped into a piece of vinyl plastic. You can almost see the grooves if you look closely at a phonograph record. It goes round and round at a certain speed. This is a 33 RPM long-playing record, and it could store about 40 minutes of information on each side, of sound information. You may even remember the old 45 RPM single song records with the big hole in the middle. That's a later, or not later, but that's another version of the phonograph record. A number of other recording devices and playback devices have also been used. There were wire recorders that used a steel wire to record information magnetically. That was a precursor of the magnetic tape. Some of you, again, you date yourselves, may remember reel-to-reel tape. Looked like that, 1/4 inch in width. It spun around, and 7.5 or 3 3/4 inches per second went by, and the information was recorded magnetically. We'll get more about how that works in Module 3. VHS tapes work similarly, although the working is a little bit more complicated. So there's something you probably remember, or some of you may remember. That kind of tape gave way to what's still in circulation, the small cassette tape, in which the tape is all contained in a cassette, an audio cassette, 1 7/8 inches per second. The tape swings by and spews out its information or gets its information recorded. So there's a audio cassette tape. And finally, the video cassette, very similar. Here is the teaching company's course, The Joy of Thinking. And the video cassette stores a half inch wide tape on 2 reels built into the cassette. And again, the medium is magnetic. The information is stored magnetically. The only difference is there are both video and audio information stored on this device. So that's a kind of history of where we've been. But today where we are is with the disc. And discs come in all shapes. Here's a classical music disc, storing classical music in audio format. Here's a disc that happens to store the instructor's manual for my physics text, the solutions to all the problems in the text. Here's a little demonstration of how GPS works, stored on a disc, how the global positioning system works. Here is the same Joy of Thinking course, now on DVD, a disc format that can store a 2-hour movie on this little plastic disc. Remarkable invention, almost miraculous in its ability to store huge amounts of information on a small region. How does that work? Well, the first thing about discs that's important to understand is that the information on a disc is stored digitally. The information on those older media I showed you, the phonograph record, the audio cassette tape, the analog video cassette tape, the information there is all stored in what's called analog format. That means the variations in the stored information correspond to actual variations in light level, actual variations in sound volume, and so forth, and they vary continuously. A CD or a DVD, and I'm going to talk mostly here in this lecture about CDs, although almost everything I say applies to DVDs, although things are just a little bit more complicated with DVDs because of the greater information storage. The information is stored digitally, and what that means is the information is ultimately stored as a sequence of answers to questions. Yes or no, 1 or 0, true or false. And those answers are clear and unambiguous. And that means something important. That means every time you play a CD, you get exactly the same thing out of it. Every time you watch a movie on DVD, you get exactly the same thing out. Unlike a phonograph record that scratches, or a magnetic tape that loses its magnetism, or transfers some of it to a nearby layer of the tape, which is why you sometimes hear a little echo when you play an old tape, particularly one that's been stored a long time. On a CD or DVD, you get exactly the same thing every time. That's because it's always unambiguous whether it's a 1 or a 0. That has what is either an advantage or a disadvantage, depending on who you are, which it means that the information on a CD or a DVD can be copied exactly, perfectly, 100% with no degradation, over and over and over and over again. If you're the recording industry, that really scares you, because it means the products you put out can be copied without any degradation perfectly. The digital information can be stored, it can be sent over the internet, it can be written to new disks, and it's identical. That's not true with analog devices. If I copy a VHS tape, the copy looks worse. If I copy a record to a tape, it doesn't get better, it gets worse. Even if I copy a record to a CD, which is probably a good thing to do with your ancient vinyl records if you'd like to preserve them, the copy is know better than what was on the record at that point. It won't get any worse from there on, even if the record deteriorates, but the record will continue to deteriorate each time you play it. So digital information has this wonderful advantage that it can be copied forever without degradation. So what does it mean that this is digital information? Well, again, all the information on a CD or DVD ultimately comes down to either ones or zeros, sequences of ones or zeros. You can think of those as binary numbers. That is, numbers in the base 2 system. Just like our system of digits uses the digits 0 through 9 to make all numbers, the binary system is even simpler. It uses the digits 0 and 1, and that's it. For example, the number 1 is 1. The number 0 is 0. The number 2 is 1, 0. 1 times 2 plus 0 times 1. And you can build up all numbers that way. Remarkably, and this is a very simple idea, but one that's often a little startling, if I pick up my disc, for example, of Brahms Symphony No. 3 here, Brahms Symphony No. 3, as recorded on this disc, is nothing but a single number. It's a very large number. It's a binary number with many, many, many digits, but all of Brahms Symphony No. 3 is nothing but one single number. And if I told you what that number was, I would tell you everything there was to know about that symphony as recorded on this disc. That's remarkable. When you go out and buy Microsoft Office to put on your computer, Microsoft Office is nothing but an enormous binary number. When you write your PhD thesis or have that paper that's due for your college course tomorrow on your computer, put it on a disc or even in your computer's memory, it is nothing but a single number. You say, well, how can something as complicated as my PhD thesis be a number? Just tell me the number. Well, I can't tell you the number. It's so long, it's got so many binary digits to it, so many ones and zeros strung together in a particular unique sequence, that if I told you that whole sequence, I would in fact have told you the entire content of your PhD thesis or term paper or Brahms symphony or whatever it is. Take a digital camera image. That's also just a big number. Again, a big binary number. Okay? How do we put the numbers on, in particular, a music CD? The numbers on a CD are stored this way. Every second, there are 44,100 measurements made of the intensity of the sound coming in. And each of those measurements is digitized, that is, converted to a digital number. It's a number, there are 16 binary bits in those numbers, which means the numbers, there are about 2 to the 16th power, or about 66,000 possible volume levels. There aren't infinitely many. No digital system has infinite variations, but there are about 66,000 possible variations in sound level. And all that happens in making a CD is we sample the incoming sound 44,100 times every second, and that information, the levels, one of 66, roughly 66,000 different levels, is then stored. Actually, the total number is 88,200 because we tend to do things in stereo, and we have 2 different channels recording 2 different sounds from different regions of the same sound source that we're trying to record. And we can code those ones and zeros in lots of different ways. They can become electrical signals, basically switches that are on or off, 1 or 0, true or false in a computer memory. More on that in Module 4. We can store them as oppositely magnetized regions on a magnetic tape. Although I've talked about magnetic cassette tapes and VHS tapes as analog devices, there are also available digital audio tapes. And this little digital audio tape is similar to a standard cassette tape cartridge. It's a little bit different, but on this tape, the information is stored digitally. Either the magnetic field points this way or it points that way, and there's no ambiguity in between. So that is another way of storing information digitally. And, of course, it can be stored as information on these optical discs I've talked about. And in that case, it's stored as spots that ultimately alter the reflection properties of the disc. And that's what I want to spend most of the rest of this lecture on, giving us a sense of how it is that this information is coded. I want to emphasize again that because the information is ultimately broken down into questions of true or false, yes or no, 1 or 0, there's absolutely no ambiguity. There's no gray area. Either it's a 1 or it's a 0, and therefore there's no way of producing interference with this information. There's no way of degrading the information. There's no way, at least in principle, of anything happening but either a 1 or a 0 comes out, and the right thing comes out all the time, whatever you put in there. There's no shades of gray in between. Well, how does it work on a CD or DVD? Well, on a commercially made CD or DVD, like the one you're watching from this course, if you're watching this course in DVD, or like this music CD, the information is actually stamped into a little metallic layer on this plastic on the disc, and it produces little tiny regions called pits, little holes, if you will, in this little tiny metallic information layer. That's done because that's a very robust method. It's a mechanical deformation, literally, of the disk. That's why we talk about stamping disks. We also talk about burning them, and I'll get to that later. That's a different process. But commercial disks are literally stamped out in these little pits. Now, these pits are tiny. They range in size from an order of 1 to 3 millionths of a meter. And I'm going to be talking a lot in this particular module about millionths of meters for reasons that will become obvious. So let me give you a little sense of scale. First of all, I'm a scientist, and one problem I always have in talking about courses for non-scientists is how far I go in giving up the scientific unit system. So I'm going to be kind of ambiguous and ambivalent about that. Sometimes I'll talk in feet and inches. Sometimes I'll talk in meters. Here's a meter stick. It's about a yard long. It's divided into fairly big divisions called centimeters, each one very roughly about half an inch, and each of those is divided into 10 little tiny regions, the smallest things you can see on here, called millimeters. A micron or micrometer or millionth of a meter is 1,000th of a millimeter. So if you take the smallest divisions you can see on this meter stick or on a metric ruler, and you think of dividing those into 1,000 parts, each of those parts is a millionth of a meter. And the pits on a CD, not a DVD, they're smaller yet on a DVD, but on a CD, they're about a half a millionth of a meter in size. A human hair, by the way, is 100 millionths of a meter in diameter. So we're talking about things that are about 100th of the diameter of a human hair. And these pits extend in a spiral track. They're about 1.5 millionths of a meter apart, and there are spiral tracks that run all the way around the disk. There's about 22,000 of them. If you laid them out straight, the total number of tracks on an ordinary CD would be about 3 miles long. Remarkable device. And the number of those pits determines how much information you can store. So it's the number of those pits that you can cram in that determines that we can store about 74 minutes of music on a typical CD, and we can store about 640 million bytes of computer information on basically the same CD. By the way, as you look at a disk from the bottom side, the business end of the disk, if you will, not the side with the label, you see these rainbows flashing off. You can't see the pits themselves. They're too small. But those rainbows are evidence that the pits are there. Why do they occur? We'll get to that in the next lecture. Let's take a look, though, at what a close-up of a CD would look like. So here's a CD, picture of a CD. Took that picture just by putting the CD on a scanner and scanning it. And if we blow that up, many, many fold, there's a little tiny spot of the CD. Let's blow that up. We see something that looks like this. This is a picture that shows a hunk of the CD, a little tiny piece of it. You see here 3 parallel tracks in those spiral tracks that are going around the CD. You see several pits. Some of them are longer. Some of them are shorter. They come in various sizes. Some of the smallest are these little round ones, and there are longer ones. The red or orange spot in the middle is roughly the size of the laser beam spot that's reading the CD. So that's how that works. That's what's going on there. A laser beam shines on this. How does a laser beam work? Well, we're going to get to that in Lecture 34. And these pits appear not because they're stamped from above. They actually appear as little raised areas. And the laser beam shines off these raised areas, and it reflects. And when it hits a flat area between these pits, all the light gets reflected off. But when it hits the edge of one of these pits, for reasons that we'll cover in more detail in the next lecture, but I'll give you a hint of now, some of the light is reflected, but some of the light interferes with itself and diminishes its level. So here's roughly what it looks like. Here are a couple of these tracks of pits. We're looking down on the top of the disk, and we shine a laser beam, and that laser beam bounces off the CD, and how it bounces depends on whether it's on a pit, on the space between a pit, or on an edge of a pit in between. You might think, by the way, well, we're going to let these pits represent digital ones and the non-pits represent digital zeros or something, but actually we let the edges represent ones and the blank space in between represent zeros, and there's a clever coding scheme that makes sure we'll never be ambiguous about this. So what happens? Well, this is a top view. Let's take a look at a side view of what's going on here. So here's a side view of a disk. And what you see here is at the top, the disk surface where the label is attached. Actually, only a short distance down below that, and this disk is quite thin. It's about a millimeter and a half thick. It's quite thin. Down just a little ways from the top is the metal information layer in which those pits have been stamped. And I've suggested that here in this drawing by the depth of the pit. And then underneath, there's a fairly thick layer of plastic, thick plastic underneath, that basically protects that information layer. In a sense, the disk is actually more vulnerable from the side with the label than it is from the side below where it's red. So what happens? So we shine laser light on the disc, comes up through the bottom of the disc, through that transparent plastic. It bounces off, and out it comes and is picked up by a photodetector of some sort in the CD player, and that information is sent to electronics that decodes it. That's what it looks like when it hits the part of the CD between pits. Here's what happens when it hits a pit edge. Some of the light bounces off the flat part below the pit. Some of it bounces off the pit itself. And notice what's happening here. Those two light waves have come out, and they are out of step. One of them has had to travel a little bit further, and as a result, for reasons I'll describe in much more detail in the next lecture, they interfere with each other, and the light is dimmed. So that is how the information has gotten stored. We have dimmer light when the pit edge is underneath the CD. And so that's basically how a CD works. And I want to show you, before I go on to talk a little bit more about the properties of these CDs, I want to show you a simple demonstration of exactly what's going on here. What I have here is a device a student of ours actually built. It was sort of a model to show how a CD works. And here is a real CD, which the student took and marked with big hunks of black magic marker to simulate the effects of these pits. Now, these things are probably 100 to 1,000 times the diameter of a human hair. And since a human hair is about 100 times the diameter of the pits on a CD, these are probably 10,000 to 100,000 times bigger than the pits on a real CD. What I have here is a little demonstration he built in which we took the motor out of a real CD drive. So that's the motor out of a CD drive, and I'm going to plunk this fake CD down on it. I have, instead of an ordinary laser, I have a laser pointer here, standard laser pointer for pointing at a blackboard, shining down on the CD, and I have a very tiny photodetector which will detect that, and the electrical signal from that photodetector is going to come out of this cable. And I'm going to look at it on a device which I want to spend a few minutes introducing you to. This is one of the most versatile of electronic instruments. It's called the oscilloscope. And if this were 10 years ago, I would be explaining it very differently. Any of you who have ever used an oscilloscope, you learned about cathode ray tubes and electron beams sweeping around and all that kind of stuff. It's all gone now in the digital era. Basically, all this device is a device that takes an electrical signal plugged into one of its 4 inputs here. It, like a CD does, it samples that signal many, many times per second and sends the level of that signal to a computer like memory in here, and then displays the results on the screen as a function of time. So what it allows you to do is look at any time-varying electrical quantity visually. And by extension, it means you can look at any other quantity that can be converted to an electrical signal. In the next lecture, for example, no, not in the next lecture, but in the last lecture in this module, we'll be looking at sounds from a microphone on this same oscilloscope. So what I'm going to do is plug into the oscilloscope the signal coming from the CD, the pseudo CD player. I'm going to turn it on and get the disc spinning. And I'm going to look at a signal. Now, because the screen on this particular oscilloscope is fairly small, we've set up a larger screen connected to the oscilloscope and seeing exactly the same thing its screen does. And we'll put that on your screen for you to see. We'll put that on the recording we're making. So I'm looking at this screen, but you're looking at an identical but larger screen that will film better. And you see a pattern of low levels and high levels. Low level there, short high level, low level, high level, low level, high level coming up. And if I take another shot at this, I'll catch it at a different part in the disc, and you see a slightly different pattern corresponding to the different sizes, the different lengths, the different times those different dark and light patches are on. So there's a pattern for a different part of the disc, there's something different, there's something different, there's something different. And the time scale here is fairly long, a matter of a good fraction of a second. On a real CD, if I were doing the same thing and looking at the raw data that were coming off the CD, I would be working at thousandths of second time scales or tenths of thousandths of seconds in order to see the same kind of thing. You might say, what does this silly fake CD sound like? Well, I can connect a microphone, a loudspeaker up to it, and you will hear that. It's not very dramatic. It isn't going to be Brahms' Third Symphony, but here's just a little loudspeaker which I will connect up. So that wasn't very exciting, but what you did hear at least was some variation in the sound. It wasn't just a monotone, and that variation corresponded again to the variations in the sizes of the pseudo pits that my student has written on here with black magic marker. By the way, if I connect the loudspeaker again, turn the device off, you hear it slowing down just as you might expect, something you don't hear from your usual CD player. So CDs are great things, and by extension DVDs are great things, and this is basically how they work. One huge advantage of CDs over previous storage systems is they're enormously immune to dust. You might think, if I'm dealing with these pits that are a millionth of a meter in size, what if I get a tiny speck of dust on the thing? How come that doesn't throw the whole thing off? If I got a tiny speck of dust on my phonograph record, it makes a scratch or a blip or something that I hear in the played music. Doesn't happen with a CD. Why not? Well, the reason it doesn't happen with a CD is because of the way that information layer works. Okay, so here's a picture. This is not to scale. At the top, you see the information layer where those pits are stamped. That's where the information is stored. And you see just a slight variation in that layer that represents the pits. Down at the bottom is the lower edge of the CD. And we're going to shine laser light on that. Now, it happens that the laser beam coming in looks something like this. It's quite wide at the place where it enters the CD. It's about a millimeter wide, about the width of those smallest divisions you can see on a meter stick. It's being focused by lenses that you don't see here in this picture outside, so it's coming in that conical kind of shape. You'll notice that it enters the disc, and then the path of the light rays change, and they do so by the process of refraction that we'll cover in a subsequent lecture, and understand how that works. And this is very carefully engineered, and the plastic of which those discs are made has to have exactly the same optical properties for all discs, so that the laser beam, again, this is not to scale, is focused down on the information layer to a size on the order of 2/1000ths of a millimeter, about 2/millionths of a meter. And you saw that on those previous pictures where I showed you the size of the laser beam against those pits. It was a little bit bigger than the pits. It was about 2/millionths of a meter. And so if I were to have a speck of dust, even a pretty big speck of dust, a good fraction of a millimeter in size, land on the CD, would have very little effect. It might cut down on the intensity of the laser beam a little bit, but unless it cuts down so much that it becomes ambiguous whether the reflected light off the disc represents a 1 or a 0, no problem at all. So these discs are remarkably immune to dust, unlike old-fashioned phonograph records. You probably have burned a CD in a CD burner, burning music CDs legally or illegally, or maybe you've burned CDs in your computers. How does that work? Here I have a recordable CD, and here I have a recordable DVD. How do those work? How do you burn these discs? Well, you literally do burn them. These recordable discs are coated typically with an organic dye, which responds not to the laser beam that reads the disc, but to a higher intensity laser. The laser is turned on to higher intensity when you burn the disc, and that darkens these dyes. And so instead of making literally physical pits in the disc, you make regions of light and dark. In fact, if you look at a recordable CD before and after you burn it, you'll find quite a difference in the color. And in fact, if you record only a small amount of the disc, you'll see the part that was recorded because there are these darker regions that play the same role as pits and reflect less light. So those are organic dyes in re-recordable CDRWs, re-recordable ones. Instead of an organic dye, it's a crystalline material whose crystal structure literally changes, and you can write over that and rechange the crystal structure, whereas the ones that use dyes, you can't do that to. So we have recordable CDs and recordable DVDs, and they allow us to make our own CDs and DVDs. They probably aren't as long-lasting or as robust as the metallic stamped CDs and DVDs that you buy commercially. Now, I mentioned I would talk mostly about CDs here. I've mentioned DVDs occasionally. What's different about them? They use smaller pits. They're more closely spaced tracks. They use cleverer, more efficient computer algorithms for compressing and storing the information. But otherwise, they're pretty much the same. They aren't the last word by any means. In 2003, a Japanese company introduced discs that can store about 30 times as much information as a standard CD and many times as much information even as a standard DVD. What allows for that much greater capacity? That's another issue that we'll want to explore in the next lecture when we talk about the properties of light and light waves. So let me end up simply by saying that these CDs and DVDs that are very much a part of our everyday lives are amazing devices, and they're made possible with the application of a whole host of physics principles, especially in the fields of waves, optics, a little bit in mechanics, a little bit in sound. And in the remainder of this module, we're going to explore in more detail those physics principles and come to understand how they affect not only the workings of these amazing discs, but also many, many other optical phenomena, from our own eyes to rainbows, to sound, to how bats catch insects, all kinds of things that involve the properties of waves. Thank you.